Hello, everyone. I hope you're having a wonderful virtual blockchain experience. I know this is unprecedented, but I hope everything's going on all right. So I'm a second-year PhD student at Cornell and Cornell Tech, advised by Ari Jules. And today, I kind of want to give you a brief overview of some pretty exciting new work on order fairness for blockchains, specifically in the context of decentralized finance. So given the short nature of this talk, my goal is not to go through like all the technical details of this, but simply to get you as pumped about this as I am. So this talk, for context, is based on a recent paper of ours, which will appear at Crypto 2020, which is joint work with Van Dang, Stephen Goldfeder, and Ari Jules, all from Cornell Tech. All right, so let's begin. So in the past couple of years, decentralized finance has been a really hot topic in the blockchain community. After all, if you can decentralize banking and trading and make it accessible to anyone in the world, why not, right? And let's just note, if this were in person right now, I would have made some joke about one of the JPMC guys in the third row rolling their eyes or something, but I guess for now, I'll let you off the hook. So anyways, coming back, here's an incomplete list of DeFi applications that have popped up on Ethereum just in the last 2 or 3 years. So decentralized finance has actually been incredibly popular in this specific blockchain camp too. Formally on the schedule, there's been one talk and one panel on DeFi, both led by the wonderful Phil Diane. And interestingly, 4 out of the 8 proposed projects in the coding track were also related to DeFi. But perhaps what I found most surprising was in a lot of the other sessions that I attended throughout the week, DeFi applications were discussed, and almost all sessions had at least a couple of questions related to decentralized finance. All right, so clearly DeFi is pretty hype right now, but there's a lot of problems that we need to solve before it becomes really useful to the public. So one of the major concerns recently that you might have come across pertains to so-called transaction reordering attacks. So of particular relevance is this paper by Phil Diane and others from Cornell and elsewhere that found thousands of instances of these like transaction order manipulation on decentralized exchanges on the Ethereum network. So for some context, there was this New York Times bestseller expose by Michael Lewis published in 2014, which brought to light a lot of high frequency trading in the early days of Wall Street. So this was when Wall Street firms spent millions of dollars to build low latency channels to the New York Stock Exchange and the NASDAQ so that they could receive information about a trade and act on it in the matter of microseconds. So it capitalized on this information asymmetry to realize small profits on a large volume of transactions. So over the years, high frequency trading has been subject to a lot of regulation, and today, I guess, it's no longer the wild beast it once was. But in some sense, this type of high frequency trading is exactly what we're seeing on decentralized exchanges today. And this is what Phil's paper found, basically. And in real world exchanges, there's not so much, so compared to real world exchanges, there's not so much regulation in these like blockchain exchanges. So it's basically the Wild West here on blockchain exchanges today. So therefore, I think it's important to use cryptography to provably prevent these new types of reordering attacks. So just to give some context, let me illustrate front running and arbitrage with a simple example. So suppose you have this user, Alice, that wants to buy one Bob's Bubble token, or BBT, courtesy of Ari Jules for the name, for $1 from the decentralized exchange. So this is the market rate for the token, and this is what Alice wants to send to the decentralized exchange to buy the token. So she submits an order to the exchange, but instead of writing 1, let's say Alice makes a typo, and she sends a transaction for $100 instead. Now what can happen is an adversary snooping on the network can immediately see this opportunity and try to sell any BBT tokens that it owns. So what's even more frightening is that Bob can also try to buy a token from the exchange at the market value of $1 and quickly sell it to Alice to make a profit. So if the adversary can reorder the transaction execution order in the exchange, then it can try to order its transactions before Alice's in order to seal the profit. So this is what we call an arbitrage opportunity. And this is basically when the adversary can change the order of transactions in the execution. So what's even more interesting is even if Alice sends a cancel order immediately after realizing her mistake or her typo, an adversarial reordering can still render this pretty inconsequential. So Phil's paper basically observed these examples of bots that sat on the Ethereum network waiting to catch favorable user transactions so that they could insert their own transactions before these users or front run them in order to make a profit. And as I mentioned in the previous example, arbitrage was the ability to buy from the exchange at a cheaper price and then turn around and immediately sell it to the user at a higher price. So what's interesting here is that all of these attacks were carried out by bots that were simply observing the network, waiting for an arbitrage opportunity. And these bots didn't really have any control over the actual consensus mechanism. So can you imagine the extent of order manipulation that an adversary can do if it itself was a consensus node or a miner, or if it was colluding or had bribed a miner node? So fair ordering is clearly a problem in decentralized exchanges. And unfortunately, this is not something that's very well handled by classical current protocols. So to put things in a little more perspective, let's try to take a step back and recall the consensus problem and security properties briefly. So abstractly, in the problem of Byzantine consensus, or building a linearly ordered log, a set of nodes receives the transactions from clients, and the goal for them is to agree on the ordering of these transactions. And this has to be done even in the presence of Byzantine or malicious nodes that can deviate from the protocol arbitrarily. So there's two standard properties that we want from a consensus protocol: consistency or safety, and liveness. So consistency guarantees that all honest nodes have the same view of the final log. And liveness, on the other hand, guarantees that the system makes progress. So in other words, new transactions that are input by clients are incorporated in the system fairly soon. So unfortunately, none of these properties says anything about the actual ordering of transactions in the final log. And consistency can be satisfied even if a single node is able to completely choose the transaction ordering. And it doesn't help that in practice, this is often very easy to manipulate. So for example, in classical protocols like PBFT, they are what we call leader-based, which means that the leader can propose any transaction ordering. This also means that an adversarial leader can arbitrarily manipulate any ordering. So we found that no previous protocol sort of satisfies our definitions of fair ordering. You might think that permissionless blockchains or proof of work style blockchains are better since they're intuitively more decentralized than classical protocols. And while this is true, even here, block miners can arbitrarily choose transaction orderings in the block that they're mining. So you could imagine a miner with a small but non-negligible mining power being able to impact the ordering of a non-negligible fraction of blocks. And this results in what we call a hidden centralization problem, specifically with respect to ordering. Classical techniques basically consider two main types of adversaries. The first one tries to break consistency by equivocating and trying to split the view of the network. And the second one tries to break liveness by trying to stall the network or partition the network. But recently, we've seen this third type of adversary that in many blockchain applications, specifically decentralized finance, where you try to break application guarantees and fair invariance by reordering transactions or manipulating the fair ordering. So we've kind of have this fair transaction ordering property to deal with this new kind of adversary. Okay, so I've talked a bit about fair ordering and why it's important. So let's get to the central question of how we define this property. So we considered several definitions in our paper, and it turns out that the most intuitive ones actually have an impossibility result. So here's the one that we settled on that is very intuitive, yet it's achievable by current protocol. It's achievable in protocols. So we call this block order fairness, which formalizes the notion of first in, first out ordering. So informally, the definition works as follows. If all nodes receive M1 before M2, then M1 should be output before or at least in the same block as M2. So M1 should never be output in a later block than M2. So one thing I'd like to point out here is that our order fairness property is strictly stronger than the designs considered in literature to prevent order manipulation. So these include techniques like censorship resistance or electing a random leader, or even threshold encryption, which orders transactions before their content is revealed. So let me talk briefly about our protocol. I won't go into too much details, but just to give you a high-level understanding. So we propose a protocol, Aequitas, which achieves this fair ordering property. And informally, Aequitas works in 3 stages. So each transaction goes through these 3 stages before being finally delivered in the blockchain. So we assume that transactions are input by clients to all of the consensus nodes. The first Aequitas stage is the gossip stage, in which nodes convey to everyone else the order in which they receive transactions. The second Aequitas stage is the agreement stage, where nodes agree on whose input orderings to use. And the third and final stage is the not so cleverly named finalization stage, where intuitively now, after the agreement stage, all nodes have agreed on the actual data they need to compute the final ordering of the transaction. So at this point, nodes can finalize the ordering through local computation without needing any extra communication. So our protocol actually builds on top of very common primitives. So we use reliable broadcast and Byzantine agreement in a sort of black box way by modifying those protocols slightly in order to construct our Aequitas protocol. So these are weak primitives that can be realized from any consensus protocol. So this results in a sort of interesting observation. Because these can be realized from any consensus protocol, we can infer that Aequitas works as a general compiler that can take any consensus protocol and transform it into one that also achieves order fairness. So I'll conclude with some open questions. The first that we'd like to work on is to generalize this to the proof of work setting. So in particular, it would be nice to come up with a definition that mixes this intuition of first in, first out ordering, but still incentivizes user to pay transaction fees in a sort of gas auction. Another interesting direction is to construct fair ordering protocol that are more efficient and possibly work in a non-black box way. So as I mentioned earlier, most of the technical details were actually left out of this talk. But if this has piqued your interest, or if you just want to learn more about our work, you should definitely reach out over email, and I have that posted on the slide. And I've also posted a link to the paper on the slide. Thank you.
Okay, thank you so much, Mahimna. I don't think we have time for a question. Maybe one quick one, but
I had one question.
Yeah.
Can you hear me? Yeah. So
yes.
Can you compare what are the trade-offs of your protocol compared to threshold-based ordering, where you only reveal once, like you only send encrypted transactions and then reveal only when a threshold number of them are available?
Very great question. It's actually pretty subtle, so maybe offline would be best, but just to give a high level intuition, in threshold encryption, you can still have a node that's colluding with a user and sequences their transaction at the top because they know the actual decryption of the user transaction. And this is something that's prevented in our definition.
Okay,
awesome.
Yeah.
Thanks a lot, Mahimna.